Dear learners, today we will be seeing about integral domains, which are a particular class of rings that have all three additional properties. Integral domains play a prominent role in number theory and algebraic geometry. The non-zero elements of an integral domain need not form a group under multiplication. In many applications, a particular kind of integral domain called a field is necessary. Let's see the definition of a unit. A unit in an integral domain is defined as an element having a multiplicative inverse. In other words, it is an element U for which there is a V such that UV equals 1. Some examples are: in a field, every non-zero element is a unit. In the ring of real or complex polynomials, or more generally, the ring K of x of polynomials over a field K, the units are the non-zero constant polynomials. In the integral domain Z of the integers, the only integers that meet this requirement are the integers plus or minus 1. Let us see the definition of associates. An element B of an integral domain is called an associate of an element A if B equals AU, where U is a unit. For example, in the integral domain of the integers, the only units are plus or minus 1, and the associates of an integer A are the integers plus or minus A. Next, the definition of zero divisor is: a zero divisor is a non-zero element A of a commutative ring R such that there is a non-zero element B belonging to R with AB equals 0. And the definition of an integral domain is: an integral domain is commutative ring with unity and has no zero divisors. Thus, in an integral domain, a product is 0 only when one of the factors is 0, that is, AB equals 0 only when A equals 0 or B equals 0. The following examples show that many familiar rings are integral domains and some familiar rings are not. For example, the ring of integers is an integral domain. The ring of Gaussian integers Z of I, which is the set of all A plus IB such that AB belongs to Z, is an integral domain. The ring Z of x of polynomials with integer coefficients is an integral domain. The ring Z of root 2, which equals the set of all A plus B root 2 such that A comma B belongs to Z, is an integral domain. The ring ZP of integers modulo a prime P is an integral domain. The ring Zn of integers modulo n is not an integral domain when n is not prime, since there exist zero divisors. The ring M2 of Z of 2 cross 2 matrices over the integers is not an integral domain, since M2 of Z is not commutative with respect to the operation multiplication. Z direct sum Z is not an integral domain because it has zero divisors. By the use of cancellation law, we can guess whether a ring forms an integral domain or not. This relation is given in the following theorem. A ring R has no zero divisors if and only if both the right cancellation law, that is, AB equals AC implies B equals C, and the left cancellation law, which is BA equals CA implies B equals to C, hold in R. Let's see the proof. First, let us assume that both the cancellation laws hold. Then, if there exists some zero divisor, let's say A, then A times B equals 0 for some B not equal to 0. But by right cancellation law, we have AB equals AC, which implies B equals C. That is, A times B is equal to A times 0, which implies B equals 0. This is a contradiction. So, there are no zero divisors. Conversely, if there are no zero divisors, then we shall prove that R is an integral domain. Since every integral domain can be embedded into a field F, A dot B equals A dot C implies B equals C. Because A is a unit in F, we can multiply by A inverse on the left side of the equation. Let us find out the characteristic of an integral domain. But what is the characteristic of a ring? Characteristic of a ring is defined as the least positive integer n such that nx equals 0 for all x in R. If no such integer exists, we say that R has characteristic 0. The characteristic of R is denoted by CHAR or char R. And the characteristic of a ring with unity, let us define that also. Let R be a ring with unity 1. If 1 has infinite order under addition, then the characteristic of R is 0. If 1 has order n under addition, then the characteristic of R is n. Now, let us see the definition of characteristic 0. An integral domain D is said to be of characteristic 0 if the relation MA equals 0 where A not equal to 0 is in D and where M is an integer can hold only if M equals 0. For example, there are such rings of integers, ring of even integers and ring of rationals which are integral domains and whose characteristic is 0. Let us see a theorem. Let R be a ring with unity and characteristic n. If n is greater than 0, then n is the least positive integer n such that n times 1 equals 0. The proof: if k is the least positive integer such that k times 1 equals 0, then for all a belonging to R and k times a equals k times 1 times a, which equals k times 1 times a, which equals 0 times a, and which is equal to 0, because anything multiplied by 0 is 0. Next, the definition of the finite characteristic. An integral domain D is said to be of finite characteristic if there exists a positive integer m such that MA equals 0 for all a belonging to D. Can you guess what will be the characteristic of an integral domain? Let us see a theorem. The characteristic of an integral domain is 0 or it is a prime number. Let us prove it. We have to show that if the additive order of 1 is finite, it must be prime. Suppose that 1 has order n and n equals st, where s is greater than or equal to 1 and n is greater than or equal to t, then 0 equals n times 1, which is equal to st times 1, which equals s times 1 and t times 1. We are expanding it and writing it so. Now, s times 1 is equal to 0 or t times 1 is equal to 0. Since n is the least positive integer with the property that n times 1 equals 0, we must have s equals n or t equals n. From this we can conclude that n is prime. For infinite integral domain, we have 1 times a equals 0 if and only if a equals 0. That is, the characteristic of an integral domain is prime or 0. What makes integral domains particularly appealing? That they have an important multiplicative group theoretic property, that is cancellation property. Usually, rings do not possess cancellation property for multiplication. It is clear from the following example. For example, let us consider Z6. In this ring, 2 multiplication modulo 3 over 6 equals 4 multiplication modulo 3 over 6 and both equal 0, because 2, 3 gives you 6, again it is divided by 6 and therefore it is equal to 0. The same goes for 4 and 3 when multiplied by multiplication modulo over 6 again yields 0. Here a is equal to 3, b is equal to 2 and c equals 4. Then a times b equals a dot c, but a is not equal to c, because when you do the cancellation law here, 2 multiplication modulo 3 equals 4 multiplication modulo 3 implies 2 is equal to 4, which we know very well to be not true. Therefore, Z6 does not satisfy the cancellation property with respect to multiplication. Once again, here we recall the relation of cancellation and integral domain. Let us see a theorem. Let a, b and c belong to an integral domain. If a is not equal to 0 and AB equals AC, then B equals C. Let's see the proof. From AB equals AC, we have A times B minus C equals 0. Since A is not equal to 0, we must have B minus C equals 0. Some special properties of integral domains are: number 1, the cancellation law holds in an integral domain. Number 2, let D be an integral domain and I be an ideal in D. Then D over I is an integral domain if and only if I is a prime ideal in D. Number 3, the characteristic of an integral domain is either 0 or prime. Here we shall see a remark. Many authors prefer to define integral domains by the cancellation property, that is, as commutative rings with unity in which the cancellation property holds. This definition is equivalent to the definitions described above. Let us move on to another important part of this module, which is field. The definition of the field is: a field is a commutative ring with unity in which every non-zero element is a unit. We have already seen about rings in detail in some of the previous modules, but this structure will help you to understand the rings better. We have seen in detail about rings in some of the previous modules, but this structure will help you to understand rings better. We know that R as a set along with two properties, let's say plus and dot, they are only merely denoted as plus and dot, they need not generally mean addition or multiplication, it is just that they are two binary operations. So, R comma plus is abelian and R comma dot is closed and R comma dot is associative. So, if these three properties are satisfied, it becomes a ring. Now, let us go a little bit further. If R comma dot as distributive property as well as multiplicative identity, it becomes ring with identity. Further, if this particular property is added, R comma dot is also commutative, if this property is added to the previously existing properties, it becomes a commutative ring with identity. And finally, if it also has a multiplicative inverse, it becomes a field. If a ring does not have 0 divisors with respect to this operation dot, then it is said to be an integral domain, and we know that every field is an integral domain, but not vice versa. So, this structure will help you to understand rings better, and so R comma plus comma dot becomes a field only when all these properties are satisfied. Let us see a theorem now. Every field is an integral domain. Now, for the proof, let D be a field. We are supposed to prove that D has no 0 divisors, but let us try proving this by proof by contradiction. Suppose there exists an A which is not equal to 0 and it is a 0 divisor. Then there exists a non-zero B in R such that AB is equal to 0. In this case, we can multiply on both sides of the last expression by A inverse to obtain B is equal to 0. Now, this is a contradiction. So, there are no 0 divisors in D and hence it is an integral domain. It is often helpful to think of AB inverse as A divided by B. With this in mind, a field can be thought of as simply an algebraic system that is closed under addition, subtraction, multiplication and division except by 0. We have had numerous examples of fields, the complex numbers, the real numbers and the rational numbers. The abstract theory of fields was initiated by Heinrich Weber in 1893. Groups, rings and fields are the three main branches of abstract algebra. But remember, the converse part of the above theorem will not always hold. It only happens in the finite case, which is described in the upcoming theorem. A finite integral domain is a field. Let us see the proof. Let D be a finite integral domain with unity 1. Let A be any non-zero element of D. We must show that A is a unit. If A equals 1, A is its own inverse, so we may assume that A is not equal to 1. Now consider the following sequence of elements of D: A squared, A cube, etc. Since D is finite, there must be two positive integers I and j such that I is greater than j and a power I equals a power j. Then by cancellation, a power I minus j equals 1. Since a is not equal to 1, we know that I minus j should be greater than 1, and we have shown that a power I minus j minus 1 is the inverse of a. Let us see another result. For every prime p, Zp, the ring of integers modulo p is a field. The proof? We have to prove that Zp has no zero divisors. So let us suppose that there exists a comma b belonging to Zp and ab equals 0. Then ab equals pk for some integer k. Then by Euclid's lemma, p divides a or p divides b. Thus in Zp, a equals 0 or b equals 0. That is, there are no zero divisors and hence it is an integral domain. We have finite integral domains are fields and Zp is a field. In general, Zn will not be a field. For example, in Z4, the element 2 does not have an inverse. That is, 2.0 is equal to 0, 2.1 is equal to 2, 2.2 is equal to 0 and 2.3 is equal to 2. Here, the multiple of 2 with every element of Z4 is a non-unit. So, Z4 is not a field in general, Zn is not a field. We can also prove that Zn is a field only when n is a prime. Let us see the result. Zn is a field if and only if n is a prime number. The proof? We have to prove that Zn has no zero divisors. Suppose that n is not a prime number. Then there exists a prime number p such that p divides n and n is not equal to p. That is, there exists a q such that 0 less than q less than n such that n is equal to 0 and this is equal to q dot p, and which implies that p is a zero divisor. That is, there exist zero divisors and Zn is not an integral domain. From the above corollary, we can conclude that Zn is a field if and only if n is prime. Let us see some examples. Z3 of I is a set of all a plus bi such that a comma b belongs to Z3. It is a field with 9 elements. Z3 of I will consist of 0, 1, 2, 1 plus I, 2 plus I, 2i, 1 plus 2i and 2 plus 2i, where I square is equal to minus 1. Elements are added and multiplied as in the complex numbers, and let us expect that the coefficients are reduced to modulo 3. In particular, minus 1 is equal to 2 is equal to I. Also, one more example, Q of root 2 is the set of all a plus b root 2 such that a comma b belongs to Q is an infinite field. Let us talk about some other fields like extension and splitting fields. Let us see the definition of an extension field. A field E is an extension field of a field F if F is not equal to E and the operations of F are those of E restricted to F. Note that every extension field is a vector space over its subfield. If E is an extension field of F denoted by E by F, then the degree of the extension E by F is equal to the dimension of E over F. The definition of the splitting field. Let E be an extension field of F and let f of x belonging to capital F of x with degree at least 1. We say that the function f of x splits in E if there are elements a belonging to capital F and a1, a2 so on up to an belong to E such that f of x is equal to a of x minus a1, x minus a2 and so on up to x minus an. We call E a splitting field for the function f of x over f if E is equal to capital F over a1, a2 so on up to an. Here f of a1, a2 so on up to an is the smallest field containing a1, a2 so on up to an and f. Let us see a lemma here. Lemma. Let F be a finite field with Q elements, and let us suppose that F is a subset of K, where K is also a finite field. Then K has Q power n elements, where n equals the dimension of K over F. Let's see the proof. K is a vector space over F, and since K is finite, it is certainly finite dimensional as a vector space over F. Suppose that the dimension of K over F is equal to n. Then K has a basis of n elements over F. Let such a basis be V1, V2 and so on up to Vn. Then every element in K has a unique representation in the form alpha 1 V1 plus alpha 2 V2 so on up to alpha n Vn, where alpha 1, alpha 2 and so on up to alpha n are all members of F. Thus, the number of elements in K is the number of alpha 1 V1 plus alpha 2 V2 and so on up to alpha n Vn as alpha 1, alpha 2 so on up to alpha n range over F. Since each coefficient can have Q values, K must clearly have Q power n elements. Let us find out the characteristic of a field in the next result. Let F be a finite field. Then F has P power m elements, where the prime number P is the characteristic of F. The proof: since F has a finite number of elements, and since n times 1 equals 0, where n is the number of elements in F, thus F has characteristic P for some prime number P. Therefore, F contains a field F naught isomorphic to ZP. Since F naught has P elements, F has P power m elements, where m is equal to the dimension of F over F naught. Let's see one more result. If the finite field F has P power m elements, then every A belonging to F satisfies A power P power m is equal to A. Let's see the proof. When A is equal to 0, the corollary is trivially true. On the other hand, the non-zero elements of F form a group under multiplication of order P power m minus 1, that is, A power P power m minus 1 equals 1 for all A not equal to 0 in F. Multiplying this relation by A, we obtain that A power P power m equals A. Let us find out the factor of the polynomial x power P power m minus x. Let's see a theorem now. If the finite field F has P power m elements, then the polynomial x power P power m minus x in f of x factors in f of x as x power P power m minus x is equal to the product of all lambda belonging to F such that x minus lambda. Let's see the proof. We have the polynomial x power P power m minus x has at most P power m roots in F, and P power m such roots, namely all the elements of F. Therefore, x power P power m minus x equals the product over lambda belonging to F of all factors x minus lambda. Now we know the factor of the polynomial. Can you guess what will be the splitting field of the polynomial? This will be described in the next result. If the field F has P power m elements, then F is a splitting field of the polynomial x power P power m minus x. The proof: by the above theorem, x power P power m minus x certainly splits in F. However, it cannot split in any smaller field, for that field would have to have all the roots of this polynomial and so would have to have at least P power m elements. Thus, F is a splitting field of x power P power m minus x. Let us discuss some theorems here. The first theorem is any two finite fields having the same number of elements are isomorphic. The proof: if these fields have P power m elements, by the above corollary, they are both splitting fields of the same polynomial x power P power m minus x over Zp, whence they are isomorphic. Let's see the next theorem. For every prime number P and every positive integer m, there exists a field having P power m elements. So let's see the proof. let x power p power m minus x belong to Zp over x. Now, this is a polynomial ring over x. Let K be a splitting field of x power p power m minus x. Let us assume F to be the set of all A belonging to K such that A power p power m is equal to A. Clearly, you can see that F will contain those elements which are the roots of this polynomial x power p power m minus x. We have to prove that F is a field. Now, how to prove this? First, let us prove the closure property. Let A comma B belong to F. Now, from this we can say that since A power p power m is equal to A, you can say that A is equal to A power p power m. This A will be in this format only, and similarly if you take another B, it will be in this format B power p power m. Therefore, AB power p power m is equal to A power p power m, B power p power m, and this is equal to AB. Therefore, we took two random elements from F A comma B and the product is also inside F. Therefore, closure with respect to one operation is done. Now, the characteristic of K is equal to P, since we already have seen a theorem saying that if there are p power m elements and the characteristic of that field is P, and therefore, now we have characteristic of K is equal to P, which implies A plus or minus B the whole power p power m. Now, from here this is equal to A, therefore, A power p power m will become A and B power p power m will become B, and therefore, we have proved that A plus or minus B will also be inside F. Therefore, we have proved the closure with respect to the second operation as well. So, both addition and subtraction, in both ways the closure holds, and therefore, we have proved the closure property, and hence F is a subfield of K, and therefore, which implies that obviously F is a field with p power m elements. Therefore, we have now proved the result. Let us see the next theorem. For every prime number p and every positive integer m, there is a unique field having p power m elements. The proof of this theorem directly comes from the above two theorems. The next result is every finite field has order p power n where p is a prime number, and every field of order p is isomorphic to Zp. There exists a unique field F of order 4 up to isomorphism. Let us see the Cayley table for the unique field F of order 4 up to isomorphism. So, the elements are 0, 1, beta, beta squared, and all these elements are in F. Let us first see the addition table of F. So, on the column left column we place all the elements 0, 1, beta, beta squared, and on the row wise we are putting 0, 1, beta, beta squared. We have already studied how to do the Cayley's table. Now, 0 plus 0, 0, 0 plus 1 is 1 and so on. So, they are straightforward. 1 plus 0 is 1, 1 plus 1 is 0 because the characteristic is 2 and therefore, it becomes 0. 1 plus beta is equal to beta squared. I will explain how this comes to be, because when 1 plus beta is equal to either 1 or beta, we can apply the cancellation law and they will get cancelled, and therefore, the values cannot be neither beta nor 1. So, the only possibilities are 0 and beta squared, but when we put 1 plus beta is equal to 0, we get beta is equal to minus 1, which does not hold true because the inverse of 1 is 1 itself and minus 1 cannot appear here. Therefore, the only possibility is beta squared. That is why 1 plus beta is equal to beta squared in this Cayley table. Similarly, we can find the values of all the other possibilities in the Cayley table. So, beta plus 0 is beta, beta plus 1 is again beta squared, and so on. So, you can refer to the table that is displayed on the screen. Similarly, let us find the multiplication table of F. Here it is very much straightforward. So, 1 times 1 is 1, 1 times beta, beta 1 star beta squared and so on. So, beta star 1 is beta, beta star beta is beta squared, beta star beta squared is 1 because again this is 4th power of unity and therefore, beta cube will become 1. We can check the values like this for other terms also. For every prime number p and every positive integer m, there is a unique field having p power m elements. Similarly, there exists a unique field having 8 elements. Consider the field Z2 of x over the ideal 1 plus x cube. Consider the field Z2 of x over the ideal 1 plus x cube, whose addition table and multiplication Cayley tables are shown on the screen. Now, there are 8 elements, namely 0, 1, x plus 1, x squared plus 1, x squared plus x and x squared plus x plus 1. So, these elements are represented on the Cayley table on both the left and the top corner, and then the 0 times table, 0 plus 0 is 1, 0 plus 1 is 1. So, that part is fairly clear. And when it comes to 1, 1 plus 0 is 1, 1 plus 1 is 0, 1 plus x is x plus 1, 1 plus x plus 1 is x. Why this is so? Because it is over Z2 and therefore 1 plus 1 will become 0, and therefore we are left with only x. 1 plus x squared is straightforward, x squared plus 1, 1 plus x squared plus 1 is again x squared only, because 1 plus 1 is again 0. 1 plus x squared plus x is x squared plus x plus 1, and 1 plus x squared plus x plus 1 is x squared plus x, because again 1 plus 1 equals 0. Likewise, we can do this for the entire 8 elements and we can find out the values, and they are displayed on the Cayley table on the screen. Similarly, let us do this for the multiplication part. Again, the 8 elements are represented: 0, 1, x plus 1, x squared plus 1, x squared plus x squared plus x plus 1, and so on. Similarly, here also we will have to check them individually for the 7 different cases. For example, let us consider the x times table. So, x times 0 is 1, x times 1 is x, x star x is x squared, x star x plus 1 is x squared plus x. But why is x star x squared is x plus 1? Again, we have to evaluate different operations, we have to check for different possibilities, all the other 7 possibilities, and then we arrive at the value x plus 1. The other operations can be done in the similar manner. Until now, we had seen about fields and some of its properties. When we talk about fields, we also have to know about subfields too. So, what is a subfield? A subfield of a field f is a subset K of f, that is a field with respect to the field operations inherited from f. Equivalently, a subfield is a subset that contains 1 and is closed under the operations of addition, subtraction, multiplication, and taking the inverse of a non-zero element of f. We had already learned about subgroup and subring tests. Similarly, here also we will have a subfield test. The subfield test. Let f be a field and let K be a subset of f with at least 2 elements. Then K is a subfield of f if for any a comma b such that b is non-zero in K, a minus b and AB inverse belongs to K. The intersection of subfields will be a subfield. Let us find it out here. Theorem: let the set of all T alpha such that alpha belongs to A be a set of subfields of the field F. Then the set theoretic intersection over alpha belongs to A of all T alpha is also a subfield of R. Proof: let P be equal to the intersection of all alpha belong to A over T alpha, then 0f the additive identity of the field and 1f the multiplicative identity of f lie in each subfield of f. Hence, it is in the intersection of f. If A comma B belongs to P, then A minus B and AB inverse lie in each subfield of f. So, A minus B, AB inverse belongs to P, which implies that P is a field. Finally, we are in the end of this session. Let us finish this session with this remark: let f be any field and P of f the intersection of all subfields of f. Then P of f, the prime subfield of f is isomorphic to Q or to one of the finite fields is at P. Conclusion. Dear learners, in this session we saw about integral domains and fields. First we have seen the definition of zero divisors and integral domains. Afterwards, we saw some examples of that and some properties of integral domains, followed by which we learnt about fields and subfields. I hope that this content session was useful to you. Thank you.